Picture drifting for 40,000 years through the cold, dark lanes between stars, and then, at last, slipping into a solar system with 8 planets, dozens of moons, and one world blazing with technology only to pass it by for a quiet, frozen shard of ice. That is what 3I, Atlas, seems to be doing. And for a moment, the void seems to listen. While Jupiter steals the headlines, trajectory analysts have been quietly refining the math. The gas giant isn't the destination, it's the sling, a gravity assist that aims the visitor toward Europa, where a subsurface ocean has remained sealed, chemically steady, and almost eerily pristine for hundreds of millions of years. Earth is loud. Let that thought settle into the starlight. Europa is quiet. If you were an ancient civilization running long-term biological fieldwork across the galaxy, which would you choose by the end of this episode? You'll see why the silence we keep hearing from space may not be absence at all, but procedure. And if this mystery has pulled you under the way it pulled me, tap like, subscribe, and stay with me as 3I, Atlas, glides toward Europa in the months ahead. Drop a comment with where you're watching from, your time zone, and your honest answer: are we watching a comet or something that knows exactly where it's going? Part 1. The news everyone missed. Something remarkable happened in the autumn of 2024, and almost nobody noticed. While headlines screamed about an interstellar visitor racing toward Jupiter, a small circle of astronomers kept updating trajectory models with data that didn't quite match the public story. The object, dubbed 3I, Atlas, became the third confirmed interstellar visitor to our solar system after 1I, Oumuamua, in 2017, and 2I, Borisov, in 2019. Even the gravity feels calmer when you imagine it. The world loves a cosmic flyby. And Jupiter makes excellent television. Gas giant encounters photograph beautifully dramatic, safe, and easy to frame, giving us something to point at without asking the harder questions. But here's what the early coverage skimmed right past. In the night, the story keeps its steady rhythm. After 3I, Atlas passed perihelion, the closest point to our sun. Later observations revealed something subtle in its track. The refinements were tiny, fractions of a degree, the kind of change you'd ignore on a road trip, but at roughly 30 kilometers per second across interstellar distances, a fraction of a degree is the difference between visiting a star system and missing it by light years. And the darkness holds its breath. Just briefly, interstellar objects follow hyperbolic orbits. They aren't bound to our sun the way planets and ordinary comets are. They arrive from elsewhere, swing through once, and leave forever. That's the script, what makes them interstellar. The public narrative latched onto Jupiter because that's where the close approach would be. And for a moment, the static seems to listen. May 2025. The media loves a countdown, but trajectory analysis isn't about where an object will be next week. It's about the full geometry of its path, the long curve through space, and what that curve implies about where it has been and where it is truly headed. Let that thought settle into the ice. When scientists model these paths, they account for gravity from every heavyweight in the system: Jupiter, Saturn, the Sun itself. These aren't minor tweaks, they're the line between prediction and reality. What emerged after perihelion wasn't alarming. It was simply odd. The trajectory wasn't behaving like a random interstellar drifter taking the easiest line through the neighborhood. Somewhere in the ocean, the path stays true. It was behaving like something that had an appointment. And before we go further, let me be clear, Earth was never in danger. The closest pass already happened. And it wasn't remotely close, millions of kilom. The breathless near-miss articles that bubbled up in some corners were irresponsible fiction. Even the orbit feels calmer when you imagine it. 3I, Atlas, never posed a threat to Earth. And anyone claiming otherwise either misunderstood orbital mechanics or was selling clicks. But taking Earth off the board doesn't shrink the story. It enlarges it. Because if it wasn't aimed at us, what was it aimed at? Gravity assists are common in spaceflight. In the horizon, the story keeps its steady rhythm. We use them to slingshot probes across the solar system all the time. Approach a planet at the right angle. Let its gravity bend your path. And you leave faster pointed somewhere new. It's elegant. It's efficient. It's how Voyager reached the outer planets and kept going. But gravity assists require precision. You don't stumble into one, you calculate it. You plan it. You execute it with intent. 3I, Atlas, is on a line that carries it past Jupiter at a specific angle, at a specific time, in a way that will reshape its path. That alone isn't strange. What's strange is what comes next. Europa, Jupiter's fourth largest moon, ice-covered. Ocean hidden. Sitting right in the projected corridor after the encounter. Let that thought settle into the sky. Not close enough to collide. Not close enough to endanger Europa itself. But close enough that, if you wanted to study Europa from a passing interstellar track, this is exactly the geometry you would choose. Most journalists don't picture orbital mechanics in 3 dimensions, somewhere in the blackness. The path stays true. They see a flat diagram, everything neatly drawn on one plane. But space isn't flat. Orbits tilt. Moons don't line up like beads. When you plot the real 3-dimensional path of 3I, Atlas, against Jupiter's moons, Europa doesn't merely happen to be nearby. Even the distance feels calmer when you imagine it. It sits in a corridor, a narrow window that the object seems to thread with uncomfortable precision. Coincidence, maybe. Astronomers dislike that word. Yet they use it. Because the universe is vast, and weird things happen. But when coincidences start stacking, timing aligning, geometry fitting, the narrative tightening, you begin to ask different questions. In the math, the story keeps its steady rhythm. Why would an interstellar object, traveling tens of thousands of years through the void, arrive on a trajectory that uses Jupiter as a gravity assist to pass by the one moon in our system that might harbor life? Europa isn't just another rock. It may be the single most promising place for extraterrestrial biology in the solar system. And the clockwork holds its breath. Just briefly, more promising than Mars, more promising than Titan, and more accessible than Enceladus, yet 3I, Atlas, will glide right past it. What keeps me awake isn't the trajectory alone, it's the quiet around it. Astronomers noticed, papers appeared, models updated, and still, the public conversation stayed locked on Jupiter, and for a moment, the emptiness seems to listen. The big, bright, obvious target. The safe story, the one that doesn't force you to wonder why something from another star might care about a frozen moon we've spent decades trying to understand. Maybe Jupiter isn't the destination. Maybe Jupiter is the alibi, the thing we're meant to stare at while something else unfolds in the background. Let that thought settle into the deep space. Something quieter, something that doesn't want attention. Not yet. Part 2. Why Earth was never the target. Let's talk about why Earth is a terrible place to study life. I know that sounds strange. We live here. Life is everywhere, forests, oceans, an oxygen-rich atmosphere so robust it has rewritten the planet's chemistry. Earth is a biological paradise. Right, yes, and that's exactly the problem. Earth is contaminated, not just by pollution, though we've done plenty of that. Contaminated in the scientific sense, compromised, noisy. If you're trying to study life cleanly, Earth is the worst laboratory, because everything is tangled with everything else. Even the quiet feels calmer when you imagine it. You can't isolate variables. You can't observe pristine processes. The moment you look at Earth's biosphere, you're looking at 4 billion years of evolutionary chaos, ecological competition, mass extinctions, and, lately, the Anthropocene, the epoch defined by humanity's overwhelming influence on the planet. In the shadow, the story keeps its steady rhythm. We've changed the climate. We've altered ocean chemistry. We've left radioactive isotopes in the rock record. We leak radio signals into space. We filled orbit with debris. Earth's biosignature is shouting into the cosmos in 10,000 contradictory voices, and the loudest voice is us. And the vacuum holds its breath. Just briefly. Now imagine you're an advanced civilization conducting biological research. You care about life, how it begins, how it evolves. what shapes it can take. Where do you go? To the planet where life has already produced a technological species that's actively reshaping its environment. Where every measurement is smeared by industry and radio chatter, or somewhere quieter. Where the experiment still runs undisturbed, Europa doesn't have those problems. And for a moment, the cosmos seems to listen. Europa is quiet. It's shielded. The ice isn't a barrier, it's armor. Jupiter's radiation is intense enough to sterilize Europa's surface again and again. But beneath the ice, in that hidden ocean, conditions are stable, chemically rich, energetically active, no radio leakage, no industrial pollution, no technological civilization interfering with the natural story. Let that thought settle into the stillness. If life exists there, it may be pristine, uncontacted, operating by its own rules. That's valuable biology as it functions. Not biology warped by intelligence. There's a concept in observational science called the observer effect. Somewhere in the far light, the path stays true. The act of measuring something changes it. In physics, you can minimize that with careful design. In biology, especially astrobiology, the observer effect is enormous. The moment a technological civilization appears, it begins altering the planet in ways that make the underlying biology harder to read. Even the cold dust feels calmer when you imagine it. We've done this to Earth. We've made it complicated, not just ecologically, which is natural, but observationally. Any biosignature we detect from Earth now comes with an asterisk. Is that oxygen purely photosynthetic? Or influenced by industry? Is that methane natural? Or agriculture and fossil fuels? Earth is mature, noisy, and technologically contaminated. In the slow time, the story keeps its steady rhythm. Europa is not. Europa represents what Earth can never be again, a pre-contact biosphere life. If it exists, running without the noise of technology, just chemistry, energy, and time. That isn't science fiction. It's scientific logic. If you want life in its purest, least disturbed form, you avoid worlds where intelligence has already started rewriting the rules, and the thin air holds its breath. Just briefly, and I want to be clear, this isn't about fear. It's not about advanced civilizations being afraid of humanity or avoiding us because we're dangerous. That's a very human, very egocentric framing. It's about protocol, about method. If you're doing long-term biological research across many worlds, you don't contaminate the sample by interacting with it. And for a moment, the blue marble seems to listen. You observe, you measure, you collect without interference. Earth doesn't need to be studied anymore. It's too late for that. Whatever happens here, happens. But Europa is still controlled, still pristine, still useful. The logic is almost elegant. If your goal is understanding life, not understanding technology, you ignore Earth completely. Let that thought settle into the frozen shell. You go straight to Europa. Because Earth is loud. Earth is complicated. Earth is a finished experiment. Europa is still running. And maybe, just maybe, something out there wants to keep it that way. Part 3, the geometry problem. Orbital mechanics is unforgiving. Space is mostly empty. But motion through it follows strict paths carved by gravity, velocity, and angle. Somewhere in the tidal pull, the path stays true. Imagine a dinner table scattered with plates, each tilted at a slightly different angle. Now imagine trying to throw a marble from one end so it passes through the center of one specific plate without touching the others. That's roughly what we mean when we talk about an interstellar trajectory intersecting a planetary moon. Even the hidden water feels calmer when you imagine it. Except the table is the solar system. The plates are moving, and you're throwing the marble from another star. 3I, Atlas, didn't originate here. It arrived from interstellar space, meaning its course was set tens of thousands of years ago by whatever gravitational nudges shaped its path through the void. In the distant sun, the story keeps its steady rhythm. The odds of a trajectory established so long ago naturally aligning with a close pass by Jupiter and then continuing toward Europa are astronomically small. Not impossible, The universe is big enough that unlikely things happen, but uncomfortable. So let's talk about what truly random interstellar paths usually look like, and the soft darkness holds its breath. Just briefly, when an object enters a star system on a hyperbolic orbit, its path is set by its entry vector and the gravitational field it encounters. Most of the time, these visitors don't meaningfully interact with planets. They pass through at angles and distances where planetary encounters are irrelevant. And for a moment, the wide dark seems to listen. When they do swing near a giant like Jupiter, the usual result is messy deflection. Jupiter is massive. Its gravity well is deep. A close pass can bend trajectories dramatically, often in ways that feel chaotic, because the geometry is so sensitive. But 3I, Atlas, isn't showing chaotic deflection. Let that thought settle into the old stars. Its post-Jupiter track looks smooth, almost purposeful, threading between gravitational influences while preserving a specific flight path. That's the geometry problem. Random tends to look messy, scattered. Irregular, unpredictable. This looks choreographed. And I need to emphasize something. Somewhere in the quiet sky, the path stays true. Unbound doesn't mean uninfluenced. 3I, Atlas, is on a hyperbolic trajectory, meaning the sun won't capture it, and it will eventually leave. But its path isn't immutable. Every massive body it passes tugs on it. The sun pulled it inward. Jupiter will bend it outward. These effects are predictable and calculable. Even the slow drift feels calmer when you imagine it. What's strange is how the alignments keep happening. Jupiter's moons orbit in a specific dance. Europa's period is about 5 days. Its position shifts constantly. For 3I, Atlas, to pass through the Jovian system, at the exact moment Europa is in the right place for a close approach, requires not only spatial alignment, but temporal alignment. In the long arc, the story keeps its steady rhythm. The object had to arrive at the right place and the right time after decades of travel through interstellar darkness, and it reaches Jupiter inside a 5-day window that places Europa in its corridor. That's not a coincidence. That's an appointment. Astronomers don't like talking about improbability clustering. It makes us sound like conspiracy theorists. And the small angle holds its breath. Just briefly, science deals in evidence, not speculation. But probability is a tool, and when you keep finding low probability events stacking on top of each other, you're allowed to raise an eyebrow. The threading trajectory, the timing alignment, the target being Europa, specifically not Io, not Ganymede, not Callisto, but the ocean moon scientists have obsessed over for decades. And for a moment, the heavy planet seems to listen. Each detail alone can be dismissed as chance. Together, they form a pattern, and patterns demand explanation. Now, here's where it gets speculative. And I want to flag that clearly there is no evidence of artificial course correction. None. 3I, Atlas isn't firing rockets. Let that thought settle into the deep well. It isn't emitting obvious thrust plumes. As far as we can tell, it's on a ballistic path shaped by gravity, but as far as we can tell, is doing a lot of work. We don't know what propulsion might exist that we can't measure. We don't know if micro-adjustments over long timescales could hide inside natural outgassing. Somewhere in the silent corridor, the path stays true. We don't know whether what we're seeing is simply the result of a trajectory planned thousands of years ago with a precision we can barely imagine. What we do know is this: the geometry is uncomfortable. It isn't proof. It isn't a smoking gun, but it's enough to make you pause and wonder whether randomness really explains what's unfolding, or whether we're watching a plan we weren't meant to notice. Even the thin line feels calmer when you imagine it. Random paths don't keep threading needles. They don't arrive at exactly the right time to meet exactly the right target. They scatter. They miss. They behave chaotically. 3I, Atlas, isn't behaving chaotically. It's behaving like it knows where it's going, and that should bother you. Part 4. Europa. In the faint glow, the story keeps its steady rhythm, the only moon that makes sense. Europa is about 100 kilometers across, slightly smaller than our moon, wrapped in a shell of water ice, maybe 15 to 25 kilometers thick. Beneath that shell lies an ocean. Not hypothetical, not maybe there's water, a confirmed global liquid ocean containing more water than all of Earth's oceans combined. And the grey ice holds its breath. Just briefly, we've known this for decades. Galileo data, in the 1,990 seconds, gave compelling evidence, and later observations strengthened it. Hubble detected water vapor plumes venting from the surface. Europa's ice is cracked and fractured, constantly resurfacing through geology powered by tidal heating. And for a moment, the sealed ocean seems to listen. Jupiter's immense gravity squeezes and flexes Europa as it orbits, generating friction heat energy. That heat keeps the ocean liquid. That energy drives chemistry, and that chemistry builds the ingredients life can use. This isn't fringe speculation. It's consensus science. Europa is among the most geologically active bodies in the solar system, despite being a frozen moon orbiting a gas giant 5 times farther from the Sun than Earth. Let that thought settle into the dark water. Let's talk about energy. Life requires it. On Earth, most life rides sunlight directly through photosynthesis, or indirectly by eating what photosynthesizes. But sunlight isn't the universe's only power source. Hydrothermal vents on Earth's seafloor support whole ecosystems with no sunlight at all. Somewhere in the ancient chemistry, the path stays true. Those vents pump heat and chemicals into the water, and life gathers there in complete darkness. Tube worms, blind shrimp, bacteria that metabolize sulfur compounds, a biosphere that doesn't need the sun. Europa may offer similar conditions. Its ocean floor is likely dotted with hydrothermal vents driven by tidal heating. Even the quiet protocol feels calmer when you imagine it. The ice above acts as a shield, protecting the ocean from Jupiter's radiation while still allowing water to circulate. Oxidants made on the surface by radiation can seep down through cracks, feeding chemical fuel below. You've got energy. You've got chemistry. You've got liquid water. You've got time, billions of years of stability. That's the recipe. In the radio haze, the story keeps its steady rhythm. That's what we look for when we search for life. Now compare Europa to the other candidates. Mars had water once, maybe oceans, but its atmosphere was stripped by solar wind. The surface is now a frozen desert blasted by radiation. Any life there is gone, or hiding deep underground where we can barely reach. And the ringed silence holds its breath. Just briefly, Enceladus, Saturn's small moon, also has an ocean and active plumes. But it's smaller, and its ocean may be less stable over geologic time. Titan has methane lakes and possibly a subsurface water ocean. But its chemistry is so alien we aren't sure what life would even look like there. Europa sits in a sweet spot. And for a moment, the lunar ice seems to listen, large enough to hold heat, active enough to stay dynamic, chemically rich enough for complex biochemistry, stable enough for billions of years of evolution. If you were designing a moon to incubate life, you'd end up with something very close to Europa. The misconception is that ice makes Europa dead. Let that thought settle into the tidal heat. People hear frozen moon and imagine sterility. But ice isn't a wall, it's insulation and protection. The surface is hostile, scoured by radiation and Jupiter's magnetosphere. But below is warmth, chemistry, possibility. Europa is already NASA's top astrobiology priority. Europa Clipper launched in October 2024 with instruments to study the ice shell, analyze plume chemistry, and map the hidden ocean's character. Somewhere in the dark vents, the path stays true. This isn't fringe science. This isn't wishful thinking. The community has reached a consensus. Europa may be our best chance to find extraterrestrial life in the solar system. Not fossils on Mars. Not amino acids in meteorites. Living. Active. Contemporary biology, right now, beneath the ice. The science is solid. The mission is funded. The instruments are flying. All of this was decided years before 3I, Atlas, entered our system. Which makes the timing interesting. We're about to study Europa in unprecedented detail. and an interstellar object is about to pass by it for the first time in recorded history. Even the chemical fire feels calmer when you imagine it. Two events in the same year, not sinister, not proof, but curious. If you were choosing a moon for life, you'd pick Europa, too. And, apparently, we're not the only ones who think so. Part 5. The Gardner Hypothesis. Directed panspermia isn't a new idea. In 1973, Francis Crick, co-discoverer of DNA's structure, and Leslie Orgel published a paper proposing that life on Earth might have been deliberately seeded by an advanced extraterrestrial civilization. They weren't joking. In the patient years, the story keeps its steady rhythm. They weren't throwing wild fantasies at the wall. They were offering a hypothesis inside the bounds of scientific possibility. The idea is simple: if a civilization becomes advanced enough that interstellar travel is feasible, and if it wants to spread life through the galaxy, the most efficient strategy isn't colony ships. And the pale plume holds its breath. Just briefly, it seeds biological packages. Microorganisms engineered to survive the journey, sheltered inside comets or asteroids, aimed at promising worlds where they might take root. You don't need faster-than-light travel. You don't need generation ships. You need patience and precision. Launch enough seeds toward enough star systems for long enough, and eventually some will find fertile ground. And for a moment, the golden data seems to listen. This is theory, not evidence, and I want that crystal clear. There is no proof that directed panspermia has ever happened on Earth, or anywhere else. But it isn't pseudoscience. It's a legitimate hypothesis with a real scientific pedigree. Now, let's extend the idea. Set seeding aside for a breath, and think instead about sampling. If you're an advanced civilization devoted to biological research, you don't just scatter life and hope. You monitor. You return. You check what's taken root. Earth's farming cultures understand this instinctively. You plant. Yes, but you also tend the garden. You observe in the quiet. You intervene when necessary. You harvest when the timing is right. What if the galaxy works the same way? Not colonization, not invasion, but stewardship. A gardener doesn't visit every day. They don't need to. They plant. They wait. And they return when the season turns. Decades pass. Centuries. Millennia. Time spans we can barely hold in our minds. But for a civilization capable of interstellar travel, time might not be the constraint we imagine. So what if 3I, Atlas, isn't an explorer at all? What if it's a gardener, coming back to check the crops? Let me paint it softly, like a slow-moving dream. Millions of years ago, something passed through this solar system. It carried biological material, microorganisms, extremophiles built to survive frozen water and long darkness. It delivered them to Europa, maybe by a controlled impact, maybe by gentle dispersal, maybe by a method we can't yet name. The organisms were tuned for that world, subsurface oceans warmed by tidal heat. Chemistry stirred in the deep, and they took root. They adapted. They evolved. They diversified. Europa became a living world, quietly growing beneath its ice, while Earth marched through dinosaurs, extinctions, ice ages, and eventually produced us. And now, millions of years later, another object arrives following a similar geometry, approaching Europa at a specific angle and at a specific time, not to seed, but to sample, to harvest, to see what has grown in the dark. This is speculation, pure hypothesis, but it is internally consistent. It can explain the trajectory. It can explain the timing. It can explain why Earth, the obvious target for any visitor, gets ignored completely because Earth wasn't planted. Europa was. We're not the garden. We're the neighboring field that grew wild. And the unsettling part isn't the idea itself. It's what it implies: intention, planning, resources, a civilization with both the capability and the patience to move biology across interstellar distances. And if they're coming back now, that suggests they've returned before periodically, quietly, without announcement. How many times has something slipped through this solar system without us noticing. How many interstellar passers-by before 3i, Atlas traced a similar corridor, brushed the same moon, and left without fanfare? Our detection only became sharp enough to spot interstellar visitors within the last decade. Oumuamua was the first confirmed case in 2017. Before that, we were essentially blind. Space is enormous, and most things pass like whispers. We're only now building the instruments to notice what might have been happening above our heads for millions of years. The Gardner hypothesis reframes everything quietly, but completely. It removes humanity from the center of the story. We're not the subject of cosmic fascination. We're not the target of alien curiosity. We're the accident, the unplanned complication. Europa is the experiment. Europa is the infrastructure. And whatever is coming to visit may not be interested in us at all. Explorers announce themselves. Gardeners don't. They arrive softly. They do their work. They leave. And unless you know what to look for, you might never notice they were there. Part 6. The comet that behaves too well. Non-gravitational acceleration is the polite way of saying the object moves in ways gravity alone can't fully explain. Comets do this constantly. They're built from ice. As they approach the sun, the ice warms and sublimates solid to gas without becoming liquid. That gas streams away, painting the tail we all recognize. But here's the catch: when gas vents unevenly, it produces thrust. Tiny thrust, but enough to nudge a trajectory over time. Most comets tumble and wobble as they outgas, spinning unpredictably, generating torque that nudges their orbits in messy directions. Predicting where a comet will be months or years later becomes hard, because you can't model the venting perfectly. Too many variables surface texture. Rotation, where the ice is buried. Comets are chaotic by nature. They don't usually trace clean ballistic arcs. 3i, Atlas, does show non-gravitational acceleration confirmed. Detected. Measured. On the surface, that makes sense. Spectroscopy points to carbon dioxide outgassing. It's acting like a comet releasing gas and feeling the gentle recoil of that release. Normal comet physics, case closed, except the acceleration isn't chaotic. It's stable, consistent, almost too consistent. Carbon dioxide dominance is unusual, though not impossible. Most comets are water ice dominated, and water sublimates in familiar temperature bands, creating recognizable activity patterns as they near the sun. Carbon dioxide sublimates at lower temperatures, so it can turn on farther out and linger longer as the object recedes. 3i, Atlas fits that profile. But here's the odd part. The outgassing seems remarkably symmetrical. The thrust doesn't produce the jittery tumbling or trajectory wobble you'd expect. It's smooth, controlled, as if the object maintains stability, even while losing material. That's difficult to explain with simple natural processes alone. When mass escapes unevenly, physics says spin should build. 3i, Atlas, doesn't appear to be doing that. Or, if it is, the rotation is so neatly balanced, it cancels the chaos almost perfectly. That is possible. Unlikely. But possible. Nature can be elegant. And here, consistency matters more than magnitude. It isn't the size of the thrust that feels strange. It's the precision. Mainstream explanations exist. Maybe the nucleus is unusually uniform. Maybe the spin rate distributes venting so evenly it self-stabilizes. Maybe our viewing angle makes messy motion look calm when it isn't. All of these are fair possibilities. Scientists aren't hiding anything they publish. They share data. They run models in the open. And that transparency is real. But this is where the discomfort creeps in when you zoom out. The anomalies begin to cluster. The trajectory is unusual. The timing is unusual. The implied target is unusual. Now the outgassing behavior feels unusual too. Each one alone can be explained. Stack them together, and the story tightens. Not proof, not evidence. Just a growing sense that the fit is too clean. Physics explains motion. It always has. Gravity, jets, orbital mechanics. We understand these frameworks well. What nature doesn't readily explain is choreography precision that keeps pointing the same way. If 3I, Atlas, were behaving randomly within ordinary comet behavior, we wouldn't be talking like this. But it isn't behaving randomly. It's behaving consistently, predictably, like it knows what it's supposed to do. I want to be careful. I'm not claiming it's artificial. I'm not claiming intelligent control. What I am saying is that the standard story, random interstellar comet passing through, starts to feel inadequate. Not wrong, inadequate. As if there's a layer we haven't modeled. A variable still hiding in the dark. Scientists live comfortably with uncertainty. They build careers refining models and finding edge cases. What unsettles them is when the edge cases all lean the same way. When multiple anomalies align toward one unlikely direction, the silence begins not from conspiracy, not from cover-up, but because saying this is weird without saying this is why risks sounding unscientific. So the papers stay neutral. The trajectory notes stay technical. The language stays sterile, safe, and carefully bounded, and the public never hears about the parts that don't quite fit the expected shape. Nature explains motion. Always. But if motion is all this is, why does it feel like intent? Why does 3I, Atlas, keep behaving exactly as it needs to? To reach Europa at exactly the right time, we've been trained to accept coincidence. But how many coincidences can stack before the word loses meaning? Part 7, Why Europa Clipper's data matters more than publicly admitted. Europa Clipper launched on October 14th. Unsettling aboard a SpaceX Falcon Heavy from Kennedy Space Center. It's on a trajectory expected to take about 5 years to reach Jupiter, arriving around April 2030. The spacecraft carries 9 instruments built to study Europa's ice shell, hidden ocean, surface chemistry, and restless geology. This isn't a quick glance. Clipper will make nearly 50 close passes of Europa, each one designed to gather targeted data from different regions. It's a slow, methodical mapping like listening to a heartbeat from many angles. Over and over, until the pattern becomes clear. The payload includes ice-penetrating radar to estimate shell thickness, mass spectrometers to sample plume chemistry, magnetometers to test the ocean's conductivity, and thermal imaging to map where heat leaks upward. This is the most sophisticated mission ever sent to an ocean world. NASA has invested over $4 billion. The scientific community treats it as one of the most important astrobiology missions in modern history. And all of this unfolds while 3I, Atlas, approaches Europa from interstellar space. The timing is extraordinary, not suspicious. Extraordinary. We planned Europa Clipper for decades. It was approved in 2015. Development took years. Launch windows are dictated by orbital mechanics. None of this was built around 3I, Atlas. Because 3I, Atlas, wasn't discovered until the mission was already funded and assembled. And yet, here we are, the most significant observational campaign in Europa's history, unfolding in the same era as the first confirmed interstellar object to pass its doorstep. Europa Clipper is designed to detect biosignatures. That's the heart of the mission, not to drill through kilometers of ice, but to look for chemical and geological fingerprints that would imply biology, amino acids in plume material, organics on the surface, heat patterns suggestive of hydrothermal activity, magnetic signatures consistent with a salty, conductive ocean. These are indirect measurements, but they're powerful. If life exists in Europa's ocean, Clipper should find hints because the instruments are sensitive. The flyby geometry is carefully planned, and the science is sound. So what happens if Clipper finds something not a headline-ready proof, but strong indicators chemistry that resists non-biological explanations, plume compositions that resemble metabolic byproducts, heat distributions that align with geologic features where biology could plausibly thrive? The discovery wouldn't be announced casually. It would be checked, rechecked, peer-reviewed, months or years of careful analysis. But the data would exist, and the implications would be impossible to ignore. And all of that would unfold while the world is still digesting the fact that an interstellar object visited the same moon. Now let's talk about what can't be discussed publicly, not because of conspiracy, but because of institutional culture. Space agencies don't speculate. They report. They publish. They stay inside what they can defend. When you spend billions in public money, credibility matters. So even if mission scientists notice something unusual, something that doesn't fit an established model, they can't just proclaim it. They have to document it, publish it, wait for consensus. That takes time. In the meantime, there is silence, professional silence meant to prevent premature conclusions and protect scientific integrity. From the outside, that restraint can look like secrecy. But there is no evidence Europa Clipper's trajectory has been changed to account for 3I, Atlas. None. The mission profile continues as planned. The sequences are set. Still, instruments are flexible. They can be tasked to observe surprises if 3I, Atlas, deposits anything, alters surface chemistry, leaves any trace at all. Clipper's sensors could, in principle, measure it, not because the mission was designed for that scenario, but because the instrumentation is sensitive enough to register anomalies. It wasn't built to hunt. Here's the quiet truth about scientific instruments. They don't only measure what you hope to see. They measure everything within their range. Spectrometers collect all relevant light. Magnetometers record every field variation. Cameras capture whatever enters the frame. The team decides what to prioritize, what to analyze first, what to publish, but the raw data remembers everything. If something unusual happens at Europa, the evidence would be there in the archive, waiting. Whether it's noticed quickly or only years later depends on attention, interpretation, and sometimes on who thinks to ask the right question. No one has to hide anything for it to remain undiscussed. Sometimes the conversation simply hasn't started yet because the public doesn't know what to ask. And the experts are trained to speak only in proofs. There's also a simple logistical gap, the overlap between people who specialize in interstellar trajectories and people who live inside Europa. Clipper data may be smaller than it should be. Coincidences slip through gaps in expertise. Patterns can emerge only in hindsight, and sometimes the most important discoveries aren't announced, they're found later. When someone rereads old data with fresh eyes and a calmer mind, Europa Clipper will return more data on Europa than all previous missions combined. 3I, Atlas, represents the first confirmed interstellar pass through the Jovian neighborhood in recorded history. Both are part of the same unfolding era of observation. If you think the two are unrelated, you're probably right, but if you're certain they're unrelated, you're not thinking like a scientist. You're thinking like someone who already decided the ending. Part 8, Harvest versus Seed, two very different threat models. Harvesting is extraction, taking samples. Collecting data. In biology, it means removing specimens or molecules from an environment for study, preservation, and understanding. On Earth, we harvest DNA from endangered species. We collect tissue samples. We store genetic material in seed banks and frozen vaults, not as violence, but as insurance, as memory. It isn't destructive in intent. It's preservation, a way to ensure biology survives even if the organism doesn't. Now scale that up. Imagine a civilization that's been seeding life across the galaxy for millions of years. Hundreds, thousands of worlds. Some attempts failed. Some thrived. Some evolved into forms no one predicted. Europa was seeded 1 million years ago, maybe longer. The microbes took hold. They adapted. They diversified. And now it's time to check the results. What survived? What changed? What's worth preserving? That's harvesting, sampling, a long-running experiment to learn how life unfolds under Europa's conditions. And it wouldn't require contact. No landing. No drilling. A close pass could be enough. Sample a plume. Collect ejecta. Analyze surface chemistry. You could gather deep biological information without ever touching the ocean itself. Seeding, by contrast, is introduction, delivering new biology to start, restart, or supplement an ecosystem. Directed panspermia in motion. If Europa's ocean were sterile, or if earlier attempts didn't take, 3I, Atlas, could be carrying a new payload, extremophiles engineered for dark oceans, tailored to Europa's chemistry. Genetic packages designed to endure cold transit. then awaken in liquid water and begin replicating. The delivery wouldn't need to be dramatic. No fiery impact. No spectacle. A release during flyby could be enough. Some material settles. Some lodges in cracks. Over time, circulation does the rest. Decades, centuries, and the seeding, if real, takes hold. Life begins. Quietly, the experiment starts. The gardener moves on and doesn't return for another million years. Both scenarios, harvesting and seeding, are speculative. Let me underline that. There is no evidence 3i Atlas is doing either. But if we're entertaining purpose, we have to separate kinds of purpose, because the implications differ. Harvesting wouldn't threaten us. It doesn't involve Earth. We're irrelevant to the process. If Tree I, Atlas, is sampling Europa, humanity isn't affected. Our biosphere isn't targeted. We're simply watching from afar, possibly unaware of what's truly happening in the shadow of Jupiter. Seeding is more ambiguous. On one hand, introducing life to Europa doesn't harm us. It's a moon gaining an ecosystem. On the other hand, it sets a precedent. It suggests advanced civilizations actively manipulate biospheres across the galaxy. And if they do it to Europa, then the questions spread outward, fast. Have they done it elsewhere? Have they ever done it here? That thought turns heavy. Quickly. Because if life on Earth was seeded, if our evolutionary history began as a directed experiment, then we aren't the crown of anything. We're the outcome. The crop, and crops, can be harvested. But notice this: neither scenario requires contact. That matters. The ethical framework of a civilization committed to long-term stewardship could prioritize non-interference. Don't contaminate your own experiment. Don't add variables by engaging the subjects directly. Observe from a distance. Measure without disturbing. That isn't fear-based avoidance. It's scientific protocol. We do the same on Earth. In protected ecosystems, we minimize human contact. Because our presence changes what we're trying to understand. Sometimes the most ethical move is to stay away. Here's the reframe. The one that lands like cold starlight. We may not be the subject. We may be the control. Earth developed life naturally, or by seeding so ancient we can't detect it now, and then produced intelligence that grew noisy, complicated, and disruptive. Europa never did. Europa stayed sealed, quiet, controlled. If you're comparing pathways life with technology versus life without it, you need both worlds. You need the planet where biology produced a civilization that alters the environment. And you need the moon, where biology, if present, remains microbial. Slow, chemically clean. Earth becomes the case study for what intelligence does to a biosphere. Europa becomes the case study for what biology does when it's left alone. Both are valuable, but only one is worth visiting, because visiting Earth would contaminate the data. Let the ecosystem unfold on its own. Observe from a distance. Collect data without interference. This isn't fear-based avoidance. It's scientific protocol. We do the same on Earth. We build nature preserves. We limit human contact with endangered species. Because we understand something simple and sobering, our presence changes what we touch. And sometimes the most ethical choice is to stay away. Here's the reframe that should chill you quietly, deeply. We're not the subject of this experiment. We're the control group. Earth developed life through natural processes, or through seeding so ancient we can't detect it anymore. Either way, we evolved into a technological civilization, and we began reshaping our planet. We became loud, complicated, unpredictable. Europa never did that. Europa stayed quiet, stayed pristine, stayed controlled. If you're running a long-term study comparing how life develops under different conditions, you need both groups. You need the world where intelligence emerged and started interfering with natural processes. And you need the world where life stayed simple, stayed microbial, stayed chemically pure. Earth is the test case for what happens when biology produces technology. Europa is the test case for what happens when it doesn't. Both are valuable. Both are worth monitoring. But only one is worth visiting, because visiting Earth would contaminate the data. We'd know something was out there. We'd react. We'd change our behavior. The experiment would be ruined. Europa doesn't have that problem. Europa won't notice, won't react, won't change. Sample it, seed it, harvest it. The experiment continues undisturbed. We're not the subject, we're the comparison, the benchmark, the cautionary tale, the example of what happens when biology goes wrong and produces intelligence too quickly. And maybe, just maybe, the gardeners would prefer Europa, so it doesn't make the same mistake. Part 9. The missing objects problem. Let's talk about detection bias. Until very recently, we had no real capability to detect interstellar objects passing through our solar system. The technology wasn't there. The survey programs weren't running. The telescopes weren't watching. Oumuamua, in 2017, was discovered almost by accident, caught by the Pan-STARRS telescope in Hawaii during a routine near-Earth asteroid survey. It was the first confirmed interstellar object ever detected, but it almost certainly wasn't the first to visit. It was just the first one we noticed. 2I, Borisov followed in 2019. Found by amateur astronomer Gennady Borisov using a telescope he built himself. Again, almost accidental. We weren't hunting interstellar visitors. We were hunting comets and asteroids. And these objects simply moved in ways local orbits couldn't explain. 3I, Atlas, was discovered in January 2024 by the Atlas Survey System, another asteroid detection program that happened to catch something on a hyperbolic path. 3 confirmed interstellar objects in 7 years. That sounds rare, but here's the catch. We only started looking 7 years ago. Before 2017, we had no confirmed detections because we had no systematic way to see them. So how many interstellar objects passed through before our eyes were sharp enough, the Vera C? Rubin Observatory rising in Chile will change everything. It's scheduled to begin operations in 2025, running the legacy survey of space and time. This isn't a targeted program, it's a sweeping, relentless scan, photographing the entire visible sky every few nights, tracking everything that moves, asteroids, comets, satellites, and interstellar objects. When Rubin comes online, our detection rate will explode. Conservative estimates suggest we could detect dozens of interstellar visitors per year once the survey reaches full stride. Dozens per year. And those are only the ones bright enough and close enough for us to catch. Smaller objects, darker objects, objects passing farther out, they'll still slip by unnoticed. But our threshold is dropping fast. We're going from seeing almost nothing to seeing a meaningful fraction of what's truly there, which raises the obvious question, what have we been missing? Interstellar objects didn't suddenly begin visiting the moment we built better telescopes. The rate didn't change. Our awareness did. So when we look at 3 detections in 7 years and project backward, the numbers start to feel uncomfortable. If the detection rate, under ideal coverage, is dozens per year, and we've only been watching for 7 years with partial coverage, how many objects passed through in the last century, the last millennium, the last million years? Now apply that to Europa. If interstellar objects have been passing through regularly, and if even a small fraction of them thread near Jupiter's moons, then statistically, some of them should have encountered Europa before. We wouldn't have noticed. We barely notice now, but the encounters would still have happened close flybys, maybe even impacts. Europa's surface is young. Geologically speaking, it constantly resurfaces itself through tectonic motion and tidal stress. Any impact scars get erased within millions of years. Evidence of past visitors wouldn't remain. The ice keeps no permanent record, which means Europa could have been visited dozens or hundreds of times, and we'd have no way of knowing. This isn't conspiracy thinking. It's statistical reasoning. If interstellar objects are common, and our solar system sees regular traffic from the dark between stars, and Europa's position makes it a plausible waypoint for encounters, then past flybys aren't just possible, they're likely. The unsettling part is the pattern. If 3I, Atlas, follows a trajectory that looks optimized for a Europa corridor, and if that isn't unique, then maybe other objects have done the same. Maybe Europa has been a waypoint for a long time, a checkpoint, a landmark along a route established millions of years ago by something patient enough to think in geologic time. The missing objects problem isn't only what we haven't seen, it's what we can't see yet. Rubin will illuminate the present and near future, but it won't tell us about the past. We're like people who just invented eyeglasses after a lifetime of being nearsighted. Suddenly the world is crisp. Suddenly we can see details we never knew existed, but those details were always there. We just couldn't see them. Interstellar objects have been visiting Europa for millions of years. We were blind to it. And now, just as our vision starts to clear, just as we develop the tools to notice what's been happening all along, we catch an object on approach. One that fits a pattern we're only now learning how to recognize. 3I, Atlas, isn't anomalous because it's visiting Europa. It's anomalous because we're finally awake enough to watch it happen. How many others passed through while we were sleeping? How many missions completed without witnesses? How many times has the gardener checked on the garden while we were still learning fire, building cities, inventing lenses too? Look up, we don't know. We can't know. But we're about to start keeping count. And that's when the real questions begin. Part 10. The one question no one asks. The Fermi paradox is simple. If the galaxy is billions of years old, and technological civilizations are even remotely common, then where is everybody? Why haven't we detected signals? Why haven't we been visited? Why does the universe look empty when the math suggests it should be crowded? Dozens of solutions exist. Maybe advanced civilizations destroy themselves. Maybe interstellar travel is impossible. Maybe they broadcast in ways we don't monitor. Maybe they're already here hiding, observing, staying silent for reasons we can't see. Most answers focus on why we haven't made contact. But what if the paradox is asking the wrong question? What if advanced civilizations aren't avoiding us specifically, but avoiding anyone who develops technology? Because technology is the thing that disqualifies you from observation. Think from their perspective. You're ancient. You've seeded life across thousands of worlds. You've been running this experiment for millions of years. Most seeded worlds stay microbial life emerges, evolves, stays simple. A few worlds grow complex multicellular life. Fewer still produce intelligence. And the ones that produce intelligence often follow the same arc tools: environment shaping, cities, industry, radio leakage, satellites. And then, inevitably, they start breaking things. Pollution, unsustainable extraction, climate disruption, weapons strong enough to erase themselves. Not always. Not every technological civilization collapses, but enough of them stumble, enough of them fail that a pattern forms. Technology accelerates change faster than biology can adapt. Civilization outpaces wisdom. Intelligence becomes dangerous, not to others, to itself. From the gardener's view, the moment a world develops technology is the moment it becomes unreliable. The data gets noisy. The ecosystem destabilizes. The experiment drifts away from controlled parameters. You can't trust the results anymore because too many variables have been introduced. Technological civilizations become statistical outliers, fascinating. Yes, worth watching from a distance. Perhaps, but no longer suitable for close study. Because the moment you interact, the moment you reveal yourself, they change. They react. They divert resources to finding you, reaching you, understanding you. The experiment is contaminated beyond recovery. So maybe the solution to the Fermi paradox isn't avoiding all civilizations, it's avoiding technological civilizations specifically. Microbial biospheres, study them closely. Sample them. Tend them. They won't notice. They won't react. They'll never know you were there. But technological civilizations, leave them alone. Let them solve themselves. Let them either mature into stability or collapse under their own weight. Either way, the outcome is data. Either way, the long experiment continues. Earth becomes the cautionary tale. We developed agriculture 10,000 years ago. Industry 200 years ago. Nuclear weapons less than a century ago. We've broadcast radio for about 100 years. In galactic time, we blinked into existence yesterday. We're infants loud, chaotic, unpredictable infants playing with matches in a dry forest. From the gardener's perspective, we're not ready, not mature, not stable. We might destroy ourselves tomorrow, or we might grow up and join whatever community exists out there among civilizations older than memory. Or we might linger in this dangerous adolescence for centuries, oscillating between brilliance and catastrophe. They don't know. We don't know. So the protocol is simple: observe, don't interfere, let the data accumulate naturally. If we survive and mature, maybe then contact becomes appropriate. But not now, not while we're still breaking things. Europa doesn't have this problem. If life exists there, it stayed microbial for eons, stable, predictable, controlled. It's the experiment done clean. Life without the complication of intelligence. Biology without technology. The garden as it's supposed to grow, untainted by tools, ambition, and the chaos intelligence brings. That's why Europa matters more than Earth. That's why an interstellar visitor might ignore us and go straight to the frozen moon. Because we're the example of what happens when the experiment goes wrong, and maybe, just maybe, the gardeners would rather Europa not make the same mistake. The one question no one asks is this: what if we're not interesting because we developed intelligence? What if we're interesting because we're a warning, a data point in a long study showing what happens when biology accelerates too quickly, when intelligence arrives before wisdom, when a species gains world-shaping power before it learns how to hold it gently? Earth is valuable, but not as a destination. As a lesson, Part 11. 2025's Exoplanet Surprise. 2025 brought unexpected clarity to the exoplanet biosignature debate. For years, astronomers used spectroscopy to analyze the atmospheres of distant worlds, searching for chemical hints of life. Oxygen was the big one. On Earth, oxygen is a biosignature produced by photosynthesis, and it would fade within millions of years without life replenishing it. Finding oxygen elsewhere felt like the holy grail, but recent studies complicated the story. Multiple teams showed oxygen can appear through non-biological processes under certain conditions. Ultraviolet light can split water molecules, leaving oxygen behind without biology. Carbon dioxide can be photochemically dissociated. Geology can release oxygen bound in minerals. Under the right circumstances, a sterile planet can mimic a living one. The implications shook the field. Suddenly, those promising oxygen detections needed reanalysis. The signature we thought meant life became ambiguous, unreliable, potentially misleading. This wasn't failure. It was science doing what science does, refining itself. But it forced a reckoning. If oxygen isn't reliable, what is the answer emerging now is brutal in its simplicity. There are no simple biosignatures, no single chemical that guarantees life. You need context, multiple data points, chemical pairings that imply disequilibrium, methane and oxygen together, sustained against chemistry's pull, phosphine where it shouldn't survive, organics in ratios that resist non-biological explanations. The search got harder, or, more honestly, it got more honest. We were never going to find life with one magic molecule. We'll find it through patient, layered observation. Which brings us back to Europa. Europa doesn't rely on atmospheric biosignatures. It isn't an exoplanet. We can't only stare from light years away and infer from spectra. Europa is here inside our reach. We can send spacecraft. We can measure directly, sample plumes, analyze chemistry in situ with instruments built to separate biology from geology. Europa represents a different paradigm entirely, not remote sensing, but direct investigation. And that makes it more scientifically valuable than almost any distant world we can only guess at. The false positive problem shifted priorities. Remote biosignatures still matter, but they're no longer the singular anchor. Ocean worlds, subsurface seas inside our solar system rose to the top. Europa, Enceladus, Titan. These aren't consolation prizes. They're premier opportunities because we can investigate thoroughly instead of inferring from thin, light, and limited context. The exoplanet surprise of 2025 reframed the conversation. It shifted attention, redirected resources, and it made Europa matter even more than it already did. Now add 3i, Atlas. To that context, the same era we accepted that remote biosignatures can deceive is the era an interstellar object approaches the most promising local target for direct biological investigation. Coincidence? Probably. This science happens on its own timeline. The false positive revelations were never scheduled around 3i, Atlas. The research unfolded on its own, naturally, yet the timing draws a narrative arc that's difficult to ignore. Just as humanity pivots toward ocean worlds, something from beyond our solar system brushes past one. Just as we admit the easy answers don't exist and direct investigation is required, an opportunity for comparison quietly arrives. Like a soft footstep in fresh snow, if Europa contains life, and if that life was ever seeded or sampled by interstellar missions, the chemistry might tell us. Not loudly, not instantly, not in a single headline, but patiently, through careful analysis that compares natural evolutionary messiness with patterns that might hint at intervention. We're not ready for that analysis yet. We don't have the data. We don't even have the full frameworks. But Europa Clipper will gather the data, and someday, someone will stare at those molecular fingerprints and ask whether they make sense as pure nature or whether they look shaped, engineered, planted. The exoplanet surprise taught us life is hard to recognize from far away, but up close, we may recognize more than we bargained for. Part 2. AI discoveries in protein folding. AlphaFold changed biology. In 2020, DeepMind's AI cracked the protein folding problem, predicting three-dimensional protein structures from amino acid sequences with unprecedented accuracy. This wasn't incremental progress. It was a true paradigm shift. Understanding how proteins fold is fundamental to understanding how life works. Proteins are biology's molecular machines, enzymes, structural scaffolding, signaling switches everything. Their function depends entirely on shape, and shape depends on how an amino acid chain folds into a precise 3D form. Before AlphaFold, determining structure demanded slow, expensive experiments, X-ray crystallography, nuclear magnetic resonance, cryo-electron microscopy. Now AI can predict structures computationally in minutes. The implications are staggering. Drug development accelerates. Disease research accelerates. Synthetic biology becomes far more practical. But there's another implication that receives less attention. AlphaFold works on Earth proteins because it was trained on Earth biology. Yet the physics of folding is universal. Chemistry is chemistry. Thermodynamics is thermodynamics. If life exists elsewhere, it might not use DNA the way we do. It might not even use the same 20 amino acids. But if it uses protein-like polymers that must fold to function, those structures still have to obey the same physical rules, which means AlphaFold-style tools could, in principle, help model alien biochemistry. The breakthrough represented decades of accumulated frustration finally resolving. Christian Anfinsen won the Nobel Prize in 1972 for showing a profound truth. A protein's amino acid sequence determines its three-dimensional structure. The information is encoded in the sequence itself. No external template required, no mystical guide hand needed, just physics and chemistry. The protein folds spontaneously toward its lowest energy configuration. We knew this, but knowing it and predicting it are very different problems. The computational challenge was immense. A typical protein contains hundreds of amino acids. Each can rotate around multiple bonds. The number of possible configurations is astronomical. Trying to brute force the lowest energy form would take longer than the age of the universe. So we leaned on experiments, crystallize the protein, fire X-rays, read the diffraction pattern, reconstruct the shape, slow, expensive, and demanding pure samples. Many proteins wouldn't crystallize at all. For decades, structural biology became a bottleneck. We could sequence genomes rapidly, but we couldn't easily see what most of those genes actually built. AlphaFold changed that, with deep learning, not by calculating every energy state, but by recognizing patterns. The AI trained on vast libraries of known protein structures. It learned what folded proteins look like, what amino acid patterns map to structural motifs, alpha helices, beta sheets, loops, turns, and once trained, it could predict structure from sequence alone with accuracy approaching experimental methods. The effects rippled through biology almost immediately. Researchers who'd spent years fighting stubborn proteins in a lab could now obtain predicted structures in hours. Drug designers could model how molecules might bind a target protein without waiting on costly experiments. Evolutionary biologists could compare structures across species and track how function changed over time. But the breakthrough goes deeper. AlphaFold doesn't merely predict Earth proteins, it captures folding as a physical process. The rules it learned are universal because physics is universal. Hydrogen bonds form the same way everywhere. Hydrophobic residues still hide from water, clustering inward, wherever water exists. So if alien life uses proteins or protein analogs, and if they fold according to thermodynamic principles, then AlphaFold-style algorithms could help model them. We might predict aspects of alien biochemistry before we ever encounter it directly. We could design smarter experiments, anticipate metabolic pathways, imagine how life might function in environments far stranger than Earth's. Extremophile research has exploded in recent years. These are organisms that thrive where we once assumed life couldn't endure: boiling acidic pools, frozen Antarctic lakes, deep ocean vents under crushing pressure, even radioactive waste. They don't just survive, they thrive. Their proteins are tuned for extremes, heat-stable enzymes, cold-adapted metabolisms, pressure-tolerant structures, chemistry that keeps functioning in hostile worlds. These are the organisms we study when we want to understand what life might look like elsewhere, because Europa's ocean isn't Earth's ocean. It's colder, buried beneath kilometers of ice, bathed indirectly in Jupiter's harsh radiation, and laced with sulfates and oxidants cycling down from the surface. Any life there would need truly extreme biochemistry. And we're starting to understand how that kind of biochemistry works. Thermus aquaticus, discovered in Yellowstone hot springs, produces enzymes stable above 90 degrees Celsius. Psychrophiles in Antarctic ice make antifreeze proteins that prevent lethal crystal growth inside cells. Deinococcus radiodurans survives radiation doses thousands of times higher than what would kill a human, using astonishingly efficient repair systems. Each adaptation is built from specialized proteins engineered by evolution for specific environmental stress. We've sequenced these organisms, mapped their proteins, traced the molecular tricks that let them persist, and now, with AlphaFold, we can begin designing new proteins from those principles. Take cold adaptation strategies, combine them with radiation resistance, add high-pressure tolerance from deep-sea life. The result could be a protein optimized for Europa's ocean. We haven't built entire organisms from scratch yet, but we're getting close. Synthetic biology already lets us design genetic circuits, engineer pathways, even craft minimal genomes. Give us a few more decades, and we may design organisms for environments as routinely as we now design software. AlphaFold-style systems can now model proteins that have never existed, hypothetical proteins shaped for specific conditions. If you wanted to engineer life for Europa, you could design key proteins computationally before you ever synthesize them: cold-adapted enzymes, high salinity tolerance, radiation-robust repair mechanisms. The design process would be iterative. Model a protein, simulate its behavior in Europa-like conditions, adjust the sequence, model again, repeat until the fit is right. Then synthesize it in the lab, test it, verify the predictions. Once your tools are validated, you scale up, design complete metabolic pathways, engineer whole organisms, test them in Europa analog chambers: high pressure, low temperature, simulated ocean chemistry. If they survive and reproduce, you've created life capable of thriving on Europa, not transplanted Earth life hoping to adapt, but purpose-built biology tuned for that hidden sea. Now, I'm not claiming anyone has done this. I'm not claiming 3i, Atlas, is carrying engineered organisms designed by alien AI. What I'm saying is simpler and stranger. The technology to do this is no longer pure science fiction. We can almost do it ourselves, and we've only had modern computing for a few decades. A civilization with millions of years of development could engineer life for any environment it chose. They could design organisms tailored to Europa's chemistry, deploy them, and be confident they'd survive and proliferate. Directed panspermia stops being a wild idea when you have the tools to make it work. It becomes engineering, practical, achievable. You don't need magic. You don't need physics-breaking technology. You need sophisticated biotech, immense computational power, and time all things an advanced civilization could possess in abundance. They could seed thousands of worlds with life optimized for local conditions. Ocean worlds get cold-adapted microbes. Desert planets get xerophiles. High-radiation environments get organisms with enhanced repair. Biology tailored to place, instead of hoping adaptation happens by accident. Protein-folding breakthroughs also matter for detection. If we find life in Europa's ocean, we'll analyze its proteins. We'll sequence its genome if it has one, and map its chemistry in detail. And if that biochemistry looks too optimized, if the proteins seem uncannily well suited for Europa's exact constraints, if the molecular logic carries hints of deliberate design, we'll eventually notice. Not quickly, not without years of debate, but patterns have a way of surfacing. Life that evolved naturally tends to look messy. It carries evolutionary baggage, vestigial features, good enough solutions. Evolution doesn't optimize, it satisfices. It finds what survives, not what is perfect. Natural proteins often contain inefficient regions, leftover sequences inherited from ancient ancestors, structures that could work better if redesigned, yet still function adequately, quietly, in the patient way biology so often does. Evolution can't redesign from scratch. It can only reshape what already exists, layer by layer. So living systems always carry their history, their constraints, their compromises, their scars. Life that was engineered, by contrast, can look cleaner, more efficient, more purpose-fit to its environment than natural selection would usually produce within any reasonable span of time. Engineered proteins would tend to show minimal waste, optimal catalytic sites, structures precisely tuned to temperature, pressure, chemistry, without so much evolutionary baggage trailing behind. If you found an organism whose proteins looked too good, too perfectly adapted, too efficient compared to what millions of years of blind tinkering should yield, that would feel suspicious. Not a verdict, not proof, but a signature, enough to justify a deeper, quieter kind of investigation. Because now we have tools to recognize the difference. We can model what natural protein evolution should look like under specific conditions and compare it to what we actually find. If the match is too perfect, if the optimization is almost unnaturally exact, that's a signal, a clue, a gentle tap on the glass suggesting intervention. Statistical analysis of protein sequences could reveal whether they likely evolved through natural selection or were designed. Natural evolution leaves fingerprints neutral mutations that don't change function. Suboptimal solutions that persist because they work well enough. Phylogenetic relationships that show gradual change over time. Designed proteins wouldn't tend to carry those same telltale features. They'd be optimized in ways that skip evolutionary intermediates. They'd lack the neutral variation real populations accumulate. They'd look streamlined, almost edited. And the AI breakthroughs in protein folding aren't directly connected to 3I, Atlas, or Europa, but they connect to the same underlying question. If advanced civilizations seed life across the galaxy, how would they do it? And if they did, would we recognize it? A decade ago, we wouldn't have. We didn't have the computational tools to analyze optimization at that depth. We didn't understand extreme biochemistry well enough to recognize engineered adaptations with confidence. We couldn't model hypothetical proteins for alien environments, but now we can. Now we're building the exact capabilities needed to detect artificial life if it exists, not by hunting for robots or starships, but by reading biochemistry closely enough to distinguish natural from designed. Europa Clipper will collect samples. We'll analyze them with the most advanced tools biology has ever developed. And if those samples contain proteins that look too perfect, too optimized, too precisely adapted to Europa's specific conditions, then we'll have an answer, not absolute proof. Science rarely offers absolute proof, but strong evidence, compelling evidence, evidence that forces us to consider possibilities we've spent centuries filing away as impossible. The timing is remarkable. We develop AI sophisticated enough to design alien life in the same era we send a mission to the most promising place to find it. Coincidence? Probably. But remarkable nonetheless. Because if Europa's ocean is inhabited, and if that life shows signs of engineering, we may finally understand what we've been looking at all along. Not random interstellar comets delivery systems. Not frozen moons, laboratories. Not cosmic silence patients, the universe running experiments. while we've only just learned how to read the results. Part trees. Advances in non-rocket propulsion physics. Momentum is conserved. That's bedrock physics. If you want to change your velocity in space, you must exchange momentum, throw something one way, and you move the other. Rockets do it by ejecting mass at high speed. The vehicle goes one way, the exhaust goes the other. Action and reaction. Newton's third law, for centuries, that felt like the only path forward. But momentum exchange doesn't require explosive thrust. It doesn't require roaring flame. There are subtler methods. Solar sails use photon pressure, light from the sun pushing, ever so gently, on a reflective sheet. The force is tiny, but it's continuous, and over long spans of time, continuity becomes power. A solar sail can build real speed without carrying fuel. Breakthrough Starshot, aimed at sending tiny probes toward Alpha Centauri, leans on this idea. Ground-based lasers would push ultralight craft to a fraction of light speed using nothing but photon pressure. No rockets, no onboard fuel, just light and time. Electric sails use the solar wind. Charged particles streaming outward from the sun interact with fields generated by long electrified tethers, producing thrust. Again, no propellant in the traditional sense, just energy to maintain the field. These aren't purely theoretical. They've been tested. They work. The thrust is small, but it's real, and there's a quiet elegance here. Traditional rockets are brute force, carry enormous fuel, burn it, hope it's enough. The tyranny of the rocket equation has haunted spaceflight from the start. Every kilogram of payload demands more kilograms of fuel, and that fuel has mass, which demands even more fuel, a steep, exponential climb. That's why chemical rockets make interstellar travel feel impossible. The numbers become absurd. But photon sails and electric sails sidestep the trap. They use resources already present in space. Sunlight is free. Solar wind is free. You just need the infrastructure to catch it. The Japanese spacecraft Ikaros demonstrated solar sailing in 2010. The Planetary Society's Light Sail 2 has been in Earth orbit since 2019, raising its orbit using nothing but sunlight. These aren't daydreams. They're working technology primitive compared to what might be possible, but undeniably real. Proof that momentum transfer doesn't require combustion. Now, consider continuous micro-adjustments. A craft under constant, gentle acceleration doesn't look like it's accelerating from far away. No bright engine burn, no obvious plume, just small velocity changes, so subtle you only see them when you measure patiently over time. If you wanted to steer something across interstellar distances, this is how you'd do it. Not with a single dramatic burn, but with a long, careful series of nudges applied over centuries, millennia, like guiding a drifting lantern through a dark corridor. Solar sails work near stars. Electric sails work in stellar wind. But what about the void between stars, where there's no sunlight worth naming, no solar wind strong enough to lean on? Here, physics turns speculative. We don't fully understand dark matter. We don't fully understand vacuum energy. We don't fully understand quantum field fluctuations or whether any of it can be harnessed for propulsion. Yet absence of understanding is not proof of absence. A civilization millions of years ahead of us might use propulsion we can't detect because we don't know what to look for. Not magic physics we haven't discovered yet. The universe is saturated with energy. Dark energy is accelerating cosmic expansion, we infer it, because distant galaxies recede faster than simple expansion alone would predict. Something is pushing, a form of energy permeating empty space driving that acceleration. We call it dark energy, but we don't know what it is or how it works. It isn't like matter. It isn't like radiation. It's something stranger, and it appears to comprise roughly 68% of the universe's energy budget. That's not a footnote. That's the dominant component of reality, and we can't fully explain it. Vacuum fluctuations create virtual particles. This isn't fantasy. It's quantum mechanics. The Casimir effect demonstrates that empty space isn't empty. Fields fluctuate. Particle-antiparticle pairs flicker into existence and vanish again. Almost immediately, the energy is there. It's measurable. We simply don't know how to tap it. The quantum foam beneath space-time seethes with activity we barely understand. If even a fraction of that energy could be harnessed, Interstellar travel stops being a fuel problem and becomes an engineering problem. And remember what we've accomplished in barely a century of flight. We went from the Wright brothers to the moon in 66 years. From Sputnik to Voyager, leaving the solar system in 36 years. Our progress has been exponential, limited more by funding and political will than by fundamental physics. Now, extrapolate not a century, but 1,000,000 years, 10 million, 100 million. What could a civilization build with that much time? What propulsion methods might emerge that we can't even conceive of because we don't yet have the mathematics to describe them? We're still wrestling with quantum field theory. We still don't have a unified framework that reconciles quantum mechanics with general relativity. We're children with building blocks trying to imagine what adults might construct with tools we've never seen. The gap could be so vast that their propulsion would look like magic indistinguishable from natural effects, because we lack the conceptual apparatus to recognize technology. 3I, Atlas, exhibits non-gravitational acceleration. We've measured it. We know it's there. The mainstream explanation is outgassing carbon dioxide, sublimating, producing thrust as it jets into space. That's reasonable. It may even be correct. But here's the uncomfortable question. If an object were using advanced propulsion we can't detect, could we reliably distinguish it from outgassing? If the thrust profile was subtle, continuous, balanced, carefully shaped to avoid obvious torque, it could look exactly like a comet behaving normally, not because it's hiding, but because our instruments aren't designed to see the difference. We measure acceleration, we measure mass loss, and we assume causation. Yet correlation isn't causation. And if thrust can be produced without a detectable exhaust, our entire framework for interpreting interstellar visitors becomes fragile. We might be looking for steam engines in a world that's moved on to silent electronics. We measure the obvious and assume we've captured everything. But what if we're missing the signal because we don't yet know what a signal looks like? I'm not claiming 3I Atlas is using exotic propulsion. I'm saying we wouldn't necessarily know if it were. The physics we understand explains the observations adequately, but adequately doesn't mean exclusively. There may be other explanations that never enter our models because we don't yet have the framework to entertain them. This isn't paranoia. It's epistemic humility, recognizing the edges of our knowledge and remembering that absence of evidence is not evidence of absence. History is full of missed realities. We couldn't see bacteria until microscopes. We couldn't detect radio waves until electromagnetism. We couldn't measure gravitational waves until LIGO. Each breakthrough revealed a layer of the world that had always been there, invisible, until we built the tools to perceive it. Propulsion technology may be in that same category, present. Functional, yet unrecognized. Non-rocket propulsion isn't science fiction anymore. It's engineering. We're building solar sails. We're testing electric sails. We're advancing ion drives. Plasma concepts. Nuclear, thermal ideas. NASA and others continue to demonstrate new propulsion approaches. The European Space Agency investigates advanced plasma drives. Private companies refine ion thrusters for satellite station keeping. In another century, we may have systems that look nothing like rockets, systems that don't guzzle fuel, systems that push gently, constantly, using ambient energy. Hall effect thrusters already hint at this. In miniature, using electricity to accelerate ionized propellant with far greater efficiency than chemical rockets, running for long durations on modest mass. And if we can imagine that now, what could a civilization 1,000,000 years ahead build? We don't know. But we should at least acknowledge that steering might be feasible, that precision might not be accidental, that maybe, just maybe, an object threading needles through our solar system knows exactly where it's going. The question isn't whether advanced propulsion is possible. Physics suggests it is. The question is whether we'd recognize it, whether our telescopes, spectrometers, and trajectory models would flag it as artificial, or simply file it away as an unusual but natural comet. Comets are diverse, different compositions, structures, activity cycles. When something doesn't fit the standard model, we expand the model. We add exceptions. We accommodate anomalies within nature because that is the conservative, responsible scientific instinct. And most of the time, that instinct is correct. Most anomalies are simply nature being more intricate than our equations expected. but some anomalies could be something else. And if we never ask the question, if we never allow for the possibility that some interstellar objects might be steered rather than ballistic, then we may never recognize them, even if they drift right past our brightest instruments. 3I Atlas might be a comet. It probably is. Yet the trajectory feels unusually precise. The timing feels unusually convenient. The target feels unusually specific. And the thrust, whatever its true source, is behaving exactly as it would need to reach Europa at exactly the right moment. That could be coincidence, or it could be the universe quietly hinting that we still haven't learned which questions to ask. Part 14. The quiet shift in SETI strategy. The search for extraterrestrial intelligence has listened for radio signals since 1960. Frank Drake aimed a radio telescope at two nearby stars and listened for deliberate transmissions. He heard nothing. But the search continued. SETI programs expanded. More telescopes, more frequency bands, more sophisticated signal processing. The assumption felt almost simple. Advanced civilizations would broadcast, either deliberately, as beacon signals meant to be found, or accidentally, as radio leakage from everyday life. After all, we leak signals constantly. Television carriers, radar sweeps, satellite chatter. Our radio bubble has been expanding at the speed of light for more than a century. So if other civilizations are similarly noisy, we should be able to hear them. But we haven't. Decades of listening. Thousands of stars surveyed. Millions of frequency channels combed through. And still, nothing. Silence. The Great Silence, as it's called. Not even a whisper. And that silence forced a reckoning inside SETI. Maybe radio isn't the right place to look. Maybe advanced civilizations don't broadcast randomly into the dark. Why would they? It's energetically expensive. It advertises your location. If you're communicating across interstellar distances, you'd use narrow, directed, encrypted transmissions invisible to everyone except the intended recipient. Accidental eavesdropping becomes essentially impossible. So SETI shifted strategy. The shift wasn't sudden. It matured over decades as the null results piled up. Every year, without a detection, forced scientists to refine the assumptions. Maybe we're listening on the wrong frequencies. Maybe we're staring at the wrong stars. Maybe the signals are there, but we aren't recognizing them because they're compressed, encrypted, or formatted in ways our algorithms can't parse. Information theory adds a chilling detail. Maximally efficient communication can look indistinguishable from random noise. If an advanced civilization optimized its transmissions for efficiency, we might be detecting them all the time without realizing they're artificial. They'd blend into the cosmic background, just more static in an already crowded sky. That realization was humbling. We'd been assuming alien signals would be obvious. Bold, clean, easy to recognize. But why would they be? A civilization speaking across light years wouldn't waste energy on redundancy and clarity built for primitive receivers. They'd compress everything down to the theoretical minimum, and that minimum can look like randomness to anyone without the decryption key. So technosignatures became the focus, not signals. Artifacts. Evidence of technology visible through indirect traces. Dyson spheres, hypothetical megastructures harvesting a star's total output. Industrial pollution in exoplanet atmospheres. Artificial illumination on a planet's night side. Heat signatures that don't fit natural processes. These are hard to hide. If a civilization is advanced enough for stellar engineering or planet-scale industry, the evidence should be detectable across light years. We've been looking. We still haven't found anything, but the search space is enormous. And then came Tabby's star, KIC 8462852, which ignited enormous excitement in 2015 when astronomers noticed bizarre dimming patterns that defied easy explanations. The star would dim irregularly, sometimes by more than 20%, in ways that didn't match planetary transits or ordinary dust clouds. For a while, the Dyson sphere idea gained traction. Maybe we were watching megastructure construction in real time. Eventually, more prosaic explanations emerged, unusual dust distributions, complex and imperfect, but natural. Still, the episode proved something important. The community was ready to take technosignatures seriously. The taboo had loosened. Speculating about artificial megastructures wasn't career suicide anymore. It was legitimate scientific inquiry. Then came the interstellar object hypothesis. Oumuamua in 2017 behaved strangely. It tumbled. It accelerated. Its shape seemed unusual, elongated, or perhaps flattened, depending on interpretation. Some scientists, most notably R.V. Loeb at Harvard, proposed it could be an artificial probe, not a natural asteroid, a defunct light sail, a derelict craft drifting between stars. The hypothesis was controversial. Most astronomers favored natural explanations: nitrogen ice outgassing, hydrogen icebergs, fractal aggregates. Each explanation had problems, but natural explanations get preference over artificial ones because of Occam's razor. And because we know natural objects exist while we have no confirmed examples of alien technology, but even so, the conversation shifted. SETI wasn't only listening for signals or scanning for megastructures anymore. It began seriously considering another possibility that interstellar objects might be probes, reconnaissance missions, surveys, automated spacecraft exploring the galaxy slowly, methodically, taking thousands, even millions, of years between stars. The logic is compelling. If you wanted to study the galaxy comprehensively, this is how you'd do it. Not with crude missions, not with faster-than-light travel. With patient automated probes, launch thousands. Send them to star systems like drifting librarians, program them to observe. Record. Transmit data across vast distances, or perhaps not transmit at all, perhaps just record and wait for retrieval. A probe passing through our solar system wouldn't need to announce itself. It wouldn't need to communicate. It would only need to collect data and move on. We'd never know it was there unless we happened to be watching at exactly the right moment with exactly the right instruments. And the math is eerie. 2. Even traveling at a small fraction of light speed, say 1%, a self-replicating probe could explore the entire galaxy in a few million years. That's nothing on cosmic timescales. If such probes exist, if any civilization ever built them, the galaxy should be saturated with their descendants by now. Every star system visited, every planet catalogued, every interesting phenomenon documented. We could be swimming in probes without realizing it because they'd be designed to observe without interfering, to blend in, to look natural, unless you examined them very carefully. SETI's language softened after Oumuamua. Statements grew more cautious. Hypotheses broadened. The possibility that we're not alone became entangled with another possibility that we've already been visited repeatedly by objects we mistook for natural phenomena, not because of conspiracy, because we weren't looking, because the difference between a comet and a probe isn't obvious from a distance, because space is vast, and we've only been watching carefully for a few years. Papers began appearing in peer-reviewed journals discussing interstellar object anomalies without immediately dismissing artificial explanations. The Galileo Project, founded in 2021, explicitly aims to search for evidence of extraterrestrial technology, both in space and in Earth's atmosphere. It's funded, it's operational, it's conducting systematic surveys. Whether you agree with Loeb's interpretations or not, the fact that the project exists and is taken seriously shows how much the field has evolved. SETI broadened from search for signals to search for any evidence of technology. That's a fundamental expansion of scope. It changes how the search is conducted, and that quiet shift aligns uncannily with the 3I Atlas timeline. We started considering interstellar objects as potential probes. We developed better detection capabilities. We began asking different questions. And then an interstellar object appeared on a trajectory that looks optimized for a Europa encounter. SETI doesn't announce discoveries lightly. If there's even a remote possibility that 3I Atlas is artificial, that conversation would happen behind closed doors not because of secrecy, but because the standards of evidence are extraordinary, and nobody wants to be wrong about something this immense. The scientific process demands extraordinary evidence for extraordinary claims. You don't announce potential alien technology based on trajectory analysis alone. You gather data, you run models, you exhaust every natural explanation, you convene panels, you submit to peer review, you wait for consensus. That takes years and it happens quietly. away from public scrutiny, to avoid premature announcements that would damage credibility if proven wrong. But the shift is real. The questions are being asked. Conferences now include sessions on interstellar object analysis that explicitly consider artificial origins. Graduate students write dissertations on probe detection strategies. Funding agencies approve grants for technosignature research. An academic infrastructure is taking shape. We're preparing for a future where identifying artificial objects becomes routine instead of controversial. Whether that future arrives next year or next century, the groundwork is being laid now. And the timing matters. Europa Clipper launches in the same era that SETI pivots toward physical artifacts. 3I, Atlas, arrives during this transition period. These aren't causally connected events. They're parallel developments, but together. They create a context where questions that would have been dismissed a decade ago are now taken seriously. Looking at an interstellar trajectory and saying, "This seems optimized for Europa," doesn't end your career anymore. It starts a conversation. The silence doesn't feel empty anymore. It feels like waiting. Waiting for more data. Waiting for better instruments. Waiting for the Vera C, Rubin Observatory, to come online and flood us with interstellar detections. Waiting for Europa Clipper to analyze that buried ocean. Waiting for someone to connect the dots that everyone can see, but nobody wants to speak aloud. The great silence might not be absence. It might be patience. The kind of patience measured in million-year intervals. The kind that doesn't need immediate. Because immediate is meaningless when you've been alive longer than most species exist. If probes have been visiting our solar system for millions of years, quietly collecting data, observing without interfering, they wouldn't suddenly announce themselves just because we finally developed technology. They'd keep doing what they've always done. Watching, recording, moving on, and we'd keep missing them unless we look very carefully with very sophisticated instruments at exactly the right time. 3I, Atlas, might be our first glimpse of that possibility. Not proof, not confirmation, just a glimpse, a suggestion that maybe, just maybe, some of the objects passing through aren't as random as they appear, that the silence we've been hearing isn't empty space at all. It's the sound of something ancient and patient doing its work while we've only just learned to listen. Part Kins. The final reframe. What happens if Europa Clipper finds life, not ambiguous chemical markers, not merely suggestive biosignatures, but definitive evidence? Organic molecules in plume samples that non-biological chemistry can't explain, DNA-like structures, protein sequences, cellular membranes, proof that Europa's ocean is inhabited. The announcement would be careful, peer-reviewed, verified by multiple independent teams. It might take months, even years, to confirm, but eventually the news would break. Life exists beyond Earth, not fossil remnants on Mars, not amino acids in meteorites, but living, active, contemporary biology within our own solar system. The implications would be staggering. Every textbook rewritten, every philosophical framework reconsidered. We would no longer be alone. The discovery would ripple through every field of knowledge. Philosophy would grapple with a universe clearly capable of producing life more than once. Religion would face questions about creation and purpose that theologians have debated for centuries in theory, but never with direct evidence in hand. Biology would gain an entirely new domain to study, a second genesis, a parallel tree of life. Even if Europa's organisms were microbial, even if they were simple compared to Earth's complexity, they would still represent a living biology beyond Earth. We could compare, contrast, learn which features of life are universal necessities and which are Earth-specific accidents of history. But then comes the question almost nobody is ready to ask. If Europa has life, and if that life shares biochemical similarities with Earth life, what would that imply? Panspermia becomes the obvious bridge. Life didn't originate independently twice inside the same solar system. It was transferred perhaps naturally via meteorite impacts, exchanging material between worlds. The early solar system was violent. Asteroids and comets hammered the inner planets. Mars and Earth exchanged material. We found Martian meteorites on Earth. The reverse must also be true. Microorganisms, protected inside rock, could survive the journey and seed multiple worlds. That's natural panspermia. Random, unguided, a consequence of orbital chaos and time. But if the biochemistry is too similar, if Europa life uses the same genetic code, the same 20 amino acids, the same fundamental molecular machinery as Earth, then independent origin becomes statistically implausible. Convergent evolution, producing identical biochemical solutions on two isolated worlds, would be a vanishingly unlikely coincidence. There are thousands of possible amino acids. Life on Earth uses 20. If Europa life uses the same 20 inches, the same configurations, with the same chirality that isn't luck, that's shared ancestry. And if Earth and Europa share biological ancestry, despite having no plausible mechanism for natural exchange too far apart, to orbits that don't intersect in a helpful way, ejecta that shouldn't travel cleanly from one to the other, then the transfer wasn't natural. It was deliberate. Someone, or something, planted it. And if 3I, Atlas, arrived in the same year we confirmed Europa life, a retroactive reinterpretation becomes almost unavoidable. Suddenly the trajectory makes sense. The timing makes sense. The geometry makes sense, not as coincidence, but as confirmation. The gardener returned when we were finally ready to see what had been growing. Not because they planned around our technology, but because, after millions of years of periodic check-ins, this visit happened to overlap with humanity reaching the ability to detect both the visitor and the garden. We still wouldn't have proof. Correlation is not causation, but the narrative would be hard to ignore. An interstellar object visits Europa the same year we confirm life there, and that life shares biochemical ancestry with Earth. At what point does coincidence stop being a useful word? At what point do we accept the simpler possibility that we're not watching random chance, but deliberate action, and that 3I, Atlas, isn't a comet? It's a mission, and Europa isn't a frozen wasteland. Its infrastructure, an ice-sheathed laboratory, a biological research station, a long-term experiment, a garden tended across timescales that dwarf human civilization. Humanity would face a choice: accept that life in our solar system was seeded by advanced intelligences and continue as if nothing has changed, or acknowledge that our existence might be part of a larger experiment we don't control, that we were never alone, that something vast, ancient, and methodical has been tending gardens across the galaxy for millions of years. And Earth is just one more world in a catalogue too large to truly comprehend. The psychological impact would be profound. Some people would find it comforting. We're part of something larger. Life is precious enough that old civilizations preserve it and spread it. Others would find it terrifying. We're not special. We're experiment subjects in a study we never consented to. The debate would rage for generations. But beneath the philosophy, a practical question would rise like a tide. Would we accept non-contact? That's the real test. Because if Europa life is confirmed, if the seeding hypothesis becomes the consensus explanation, the next question is obvious. Why haven't they contacted us? And the answer would sting with clarity: because we're not the garden. We're the control group, the comparison case, the world that developed technology and became too noisy to study cleanly. We'd want to reach out, to communicate, to demand acknowledgement. Human nature craves reciprocity. If someone's been watching us, nudging our system, tending biological experiments in the neighborhood of our world, we'd want answers. We'd want dialogue. We'd want to know why. Why seed Europa? Why not contact Earth? What's the purpose? The plan? Are we in danger? Are we valued? Do we matter at all in their calculations? But what if they don't want that? What if their protocol is non-interference, non-inference, because revealing themselves would contaminate the very experiment they've been running longer than our species has existed? Contact changes everything. The moment we know we're being observed, we behave differently. The experiment is compromised. The data becomes unreliable. From their perspective, staying hidden isn't malicious. It's methodological rigor, scientific integrity. The same reason we don't make contact with uncontacted tribes on Earth, not because we fear them, but because contact would irrevocably alter their culture, their development, their trajectory. Once exposed to modern tools and ideas, they can never return to their previous state. The observation destroys what it sought to observe. Advanced civilizations might apply the same logic to us. Contact would contaminate, so they abstain, and their patience is something we can't easily comprehend. We think in years, decades if we're careful, centuries if we're building monuments. The oldest continuously operating institutions on Earth are barely 2,000 years old. Our longest-term thinking is climate projections maybe 200 years ahead. Beyond that, we barely try. Our brains aren't wired for deep time. Evolution never needed to give us millennia as a native language, because nothing in our ancestral world moved on those scales. But for a civilization millions of years old, time would feel different. Waiting another 1,000 years to see how Earth's technological phase resolves would be trivial, a rounding error, an eye blink. Checking Europa once every 100,000 years could be routine, a quiet maintenance interval, a scheduled revisit. Nothing urgent. They're not in a hurry. They don't need to be. They've outlived stars. They've outlasted empires. They've watched worlds bloom and fade and bloom again. They've seen species rise toward intelligence, build civilizations, and either transcend or collapse. With enough data, individual worlds stop being unique. They become statistics. Examples. Data points in a distribution or a blip, an anomaly. Interesting, but not urgent. Earth is one of how many thousands of seeded worlds, one of how many hundreds that developed complex life, one of how many dozen that produced technological intelligence. We're not unprecedented. We're not special. We're a recurring pattern, playing out along familiar rhythms. And if we destroy ourselves, that's data too. One more point in a long study of what happens when biology produces intelligence before wisdom. They won't intervene. They won't save us. Not because they're cruel, but because intervention would invalidate the experiment. You don't alter the outcome just because you dislike where it's heading. You observe, you record, you learn, and you apply those lessons to future gardens, future worlds, future experiments. Our failure, if it comes, would inform how they seed life elsewhere. Do they engineer limits on technological acceleration? Do they introduce cultural or psychological constraints that slow a civilization before it outruns its own maturity? Or do they accept that intelligence is inherently unstable, that most technological species eventually collapse, and that this is simply the cost of running the experiment? The final reframe isn't really about aliens. It's about us, about what it means to realize you're not the center of the story, that the universe has been running experiments for eons, and humanity is a footnote. Europa is the main text. The ocean beneath the ice is where the work is happening, the careful tending, the patient observation, the long study of life developing in isolation. Free from the contamination of intelligence, we're just the observers who finally woke up enough to notice. 3I, Atlas, passed through our solar system. Maybe it was a comet. Maybe it was something more, but it pointed toward Europa with uncomfortable precision. And whether it was delivering seeds or collecting samples, whether it was checking on an old garden or planting a new one, the message is the same. Life doesn't need us. The universe is patient, and the gardeners don't announce themselves. They don't need to. They do their work quietly, efficiently, across timescales that make human civilization look like a blink. And then they leave. Explorers announce themselves. They make contact. They communicate. They want to be known. It's the nature of exploration. You plant flags. You send messages. You establish presence. But gardeners don't. They plant, they tend, they harvest, and they move on to the next field, leaving the garden to grow in silence. The distinction matters. It explains the Fermi paradox. It explains the great silence, not because advanced civilizations don't exist, but because the ones who last, the ones who survive for millions of years, are the ones who learn patience, who learn to observe without interfering, who learn that the deepest discoveries come from watching ecosystems develop naturally, not from imposing themselves on every world they encounter. Maybe that's what we saw. Maybe 3I, Atlas, was never here for us. Maybe it never even noticed we existed. Its sensors were aimed at Europa, its instruments calibrated for subsurface oceans, and faint chemical biosignatures drifting up through ice and plume. Earth was background noise, a contaminated sample already catalogued, already understood, no longer interesting because we crossed the threshold into technology, and everything that follows becomes disturbingly predictable. Maybe we're only beginning to understand that the question isn't whether we're alone, it's whether we matter enough to be worth contacting. And the answer, uncomfortable as it is, might be no. Not yet. Not until we prove we can survive our own intelligence. Not until we stabilize, mature, demonstrate that technology won't burn us down the way it may have burned down countless others before us. The gardeners are watching. They've always been watching. But they won't intervene, won't help, won't reveal themselves, because doing so would ruin everything they've worked for. The silence, the great cosmic silence we've tried to fill with radio telescopes and hope, might not be absence at all. It might be protocol, the sound of gardeners working quietly, patiently, while we watch from the wrong side of the fence, finally aware enough to see the work being done, but not important enough to be invited in. 3. Atlas, came and went. Europa awaits investigation, and somewhere far beyond our ability to detect, the gardeners continue their rounds, tending gardens across the galaxy, checking experiments that span geological epochs, collecting data that will shape decisions about worlds we can't imagine. And we're left here, looking up at the stars, finally asking the right questions, but not quite ready for the answers. Not yet. Maybe not for a long time. But we're learning. We're watching. And perhaps that's the first step toward maturity, realizing we're not alone, and understanding why we're still waiting for an invitation that may never come.